Hello, everyone. In this section of Electronics 1, we will introduce the operating concept of bipolar junction transistors, or BJT devices. First, let us introduce the structure of a BJT. A BJT is a three-terminal device. The three terminals are called the emitter, the base, and the collector. Inside a BJT, there is one PN junction between the base and the emitter, and another PN junction between the base and the collector. Therefore, a three-terminal device with two PN junctions can be built using two doping structures, an NPN structure or a PNP structure, as shown in the figure. Although the structure looks symmetric in the simplified diagram, an actual BJT is not symmetric because the doping concentrations are different. In particular, the emitter and collector usually have very different doping concentrations. Next, we introduce the operation modes of BJT devices. Since a BJT contains two PN junctions, and each PN junction can be either forward biased or reverse biased, there are four possible bias combinations. The first and most important operating mode is the active mode. For both NPN and PNP BJT devices, the BE junction must be forward biased. As introduced earlier for a PN junction, current begins to appear when the forward bias is roughly above 0.4 volts, and a noticeable conduction current usually occurs at around 0.7 volts. The BC junction is mainly reverse biased. If the BC junction is slightly forward biased, but the forward bias is less than 0.4 volts, the device can still be treated as operating in active mode. Compared with active mode, if the two junction bias conditions are reversed, the BC junction becomes forward biased, while the BE junction becomes reverse biased. This condition is called reverse active mode. In practice, this often happens when the emitter and collector terminals are connected in the wrong positions. The third mode is saturation mode. If both PN junctions are forward biased and the forward bias across the BC junction is higher than about 0.4 volts, the BJT is said to operate in saturation mode. In other words, if the BC forward bias is still below about 0.4 volts, the device can still be regarded as operating in active mode. Finally, if both PN junctions are reverse biased, there is essentially no conduction current. This condition is called cutoff. Now let's discuss the normal active mode operation of an NPN BJT. As mentioned earlier, in active mode, the PN junction between the base and the emitter is forward biased, while the PN junction between the base and the collector is generally reverse biased. Before analyzing the BJT, let us briefly review a forward biased PN junction. As shown in the figure, majority carrier holes in the P-type semiconductor are injected into the N-type semiconductor by the electric field under forward bias. After injection, these holes diffuse and recombine with majority carrier electrons in the N-type region, so the excess carrier concentration gradually returns to the thermal equilibrium value with distance. Similarly, majority carrier electrons in the N-type semiconductor are injected into the P-type semiconductor, diffuse there, and recombine with majority carrier holes in the P-type region. The hole motion from the P-type side to the N-type side produces current toward the right. The electron flow is toward the left, but because electrons are negatively charged, its contribution to the conventional current is also toward the right. Therefore, a forward-biased PN junction produces a conduction current from the P-type side to the N-type side. To obtain a noticeable conduction current, the injected carrier concentration gradient must be large enough. In general, current begins to appear when the forward bias is greater than about 0.4 volts, as shown in the IV characteristic curve. When the conduction current becomes large, the forward bias is usually around 0.7 volts. Therefore, for DC circuit analysis of a forward-biased diode, we can use the 0.7 volt constant voltage drop model for quick estimation. When a PN junction is reverse biased, the minority carrier concentration near the edge of the depletion region decreases exponentially because of the reverse bias electric field. The minority carriers in the neutral regions still create a diffusion current due to the concentration gradient, but this current is very small, usually below 1 picoampere. Therefore, under reverse bias, a PN junction is considered non-conducting, and its equivalent circuit is an open circuit. Now, let's look at an NPN BJT. From the structure, it may seem like two PN junctions are simply connected together. The base emitter junction is forward biased, and the base collector junction is reverse biased. So, can we analyze the internal carrier concentration profile by simply connecting the two PN junction profiles introduced earlier, as shown in the figure? However, from the circuit symbol on the right, if an NPN BJT were just two PN junction diodes connected back to back, there should be no conduction current because the one-way current directions of the two diodes are inconsistent. So where is the key difference? The key is the width of the base region. In a BJT, the base width, WB, is very narrow. This important condition makes the device behavior different from two reverse-connected diodes. Near the emitter side edge of the base depletion region, the minority carrier concentration increases exponentially because of the forward bias. Near the collector side edge of the base depletion region, the minority carrier concentration decreases exponentially and approaches zero because of the reverse bias. When the base is very narrow, the concentration profile across the base becomes approximately linear instead of exponential, as shown in the enlarged view. Next, let us analyze the current components in an NPN BJT, as shown in the figure. We first look at the base emitter junction. The BE junction is forward biased, so electrons in the N-type emitter are driven by the electric field into the P-type base region and then diffuse through the base. At the same time, holes in the P-type base are driven into the N-type emitter and also diffuse there. Therefore, the electron current injected from the emitter into the base plus the hole current injected from the base into the emitter together form the total emitter current, IE. Next, let us examine the base collector junction. Since the BC junction is reverse biased, most electrons injected from the emitter pass through the neutral base region and are swept by the electric field in the BC depletion region into the collector, forming the collector current. Only a small fraction of these electrons vanish through recombination with majority carrier holes in the base, creating the base recombination current. The hole diffusion current from the collector region is extremely small under reverse bias and can be ignored. Therefore, the collector current, IC, is mainly the electron current injected from the emitter into the base and then swept into the collector by the electric field. The base terminal current, IB, consists of the recombination current just described, plus the hole current injected from the base into the emitter under the forward-biased BE junction. Finally, we can summarize the current components of the NPN BJT as shown in the center of the slide. A large number of electrons are emitted from the emitter, which is why this terminal is called the emitter. These electrons pass through the narrow base region. A small fraction of them vanish through recombination with holes in the base, while most of them are collected by the collector, which is why this terminal is called the collector. The hole current mainly occurs at the base emitter junction, where holes are injected from the base into the emitter under forward bias. The very small hole diffusion current from the collector region can be ignored. As a result, the emitter current IE is defined as flowing out of the terminal, while the base current IB and collector current IC are defined as flowing into the device. For IB, both the electron current contribution and the hole current contribution are into the base terminal. For IC, the electron current contribution is also into the collector terminal. After discussing the current components of an NPN BJT, shown in the upper figure, let us look at a PNP BJT, shown in the lower figure. The operating principle is the same, but the carrier type is different because the doping structure is different. In active mode, the BE junction must still be forward biased. A large number of holes are emitted from the emitter, pass through the narrow base, and a small fraction of them vanish through recombination with majority carrier electrons in the base. Most holes are then injected into the collector region and collected there, forming the collector current, IC. The electron current mainly occurs at the base emitter junction, where electrons are injected from the base into the emitter under forward bias. Therefore, in a PNP-BJT, the emitter current IE is defined as flowing into the terminal, while the base current IB and collector current IC are defined as flowing out of the device. Overall, NPN and PNP-BJT devices operate by the same mechanism. The differences are the carrier type and the corresponding current directions. This concludes the introduction to the operating concept of bipolar junction transistors, or BJT devices. Please look forward to the next lecture. See you next time. Bye-bye.